Hello, everybody. I would like to thank Jan and the organizers to allow me to talk about active tectonics in the Alps. When we were looking the presentation of Marie-Luce with Hervé, we was thinking, why study active tectonics in the Alps? It's so easy to, it's so beautiful to stay in Asia. But I have two answers. The first is that nevertheless, we have nice objects. If I told you that these faults were in Tibet, probably you would believe me much more easily. And the second is that we can study other processes concerning the earthquake cycle that in this really low context of converging plates, it's a particular setting to study these secondary effects, forces. So my objective with this talk is to bring you some new data that we have been studying for the last few years, and ask you some questions. I'm a geomorphologist, geologist, but I'm hungry of other techniques and other data. So if you have answer to this question, I'm very pleased to discuss with you. But before to talk Alps, just two words about the Asia, because I would feel alone not to talk of that. And this allows me to talk about the fact I have two common points with Paul Tapponnier. I'm not a student of him, but as him, I have two double consonants in my surname, which is often a problem for the administration and the mass. And the second is that we were in Montpellier, both of us. Okay, not at the same time, but we experienced a lot in this Montpellier laboratory. And of course, if I started to study tectonics in Mongolia, well, it's because these pioneer studies allowed to focus the tectonic input on Central Asia and up to these faults 2,000 kilometers north of the Himalaya. So here there is a nice picture of the seismicity of Mongolia of the last century from Antoine Schlup, Thesis, and his students and co-authors. And so you see, in this century of seismicity, there are 4 big earthquakes of magnitude 8 or something like that. And I was thinking that if we had this picture 1 century before, probably we would observe like a desert of seismicity, because most of these earthquakes are due to the big earthquake that happened in this century. And so probably this is the talk of this morning showed this. We know that this big earthquake happened every 2, 3, 4,000 years. And so probably most of the time, the situation is this. And so this is my link with the Alps. The Alps, the Western Alps, are this seismicity, okay? These are the last 30 years of a record. And this seismicity, so here we have magnitude 2, 3, 4, looks like intense seismicity, but these are all small earthquakes compared to what we are discussing since 2 days. And when you look at Mediterranean context, on the last century, you see, well, is the Aegean Sea, where the crisis ongoing is active there. And when you see the Alps, there are some 4, some 5, but that's it. So my question, and it's a question, I know I have no answer, is what about if we have the look in the past of these Alps, larger than 100 years, and maybe in this context of low, moderate seismicity, we could observe some big ones that scramble a bit our vision of this belt. But these are all to be demonstrated or imaginary, There's only one which is real here, is this one, because it's in front of my birthplace. So I know this exists, and it's 150 years ago. And so we are not talking about 7, 8 or else, but even for magnitude 6 or 6.5, the seismic hazard and the geodynamics in the Alps could change our vision. So my, let's say, aim is to try to see if this big earthquake exists.
Just for clarity.
Yeah.
You suggesting these earthquakes might be aftershocks of earthquakes that are historic or prehistoric?
You talk about Mongolia or here?
Oh, here.
Here. No, but I can develop the reasoning. No, for the moment, I don't say anything. Thanks for the question. So just to situate again the context, we are in the Alps. This is the geological map of the Alps, and you see that this is the Penninic front, which is one of the main thrust fault that was active in the Alps, which is seen as has been demonstrated yesterday by the tomography. And so this is the subduction between Europe and Apulia plates. And so this is where the two arcs, you can see at least two arcs of seismicity are localized on. Okay? But you also see that all these earthquakes are mainly normal and strike-slip. Okay? So I go back to my picture. So this is the approximate translation in Mongolian of two very known crystalline massive in the Alps, which are the Aiguille Rouge and Argentera. And I think everybody can see the nice scarp all along here and there, which cannot be interpreted in other terms of tectonic deformation. I try to explain you why. So if we start, just to situate these faults are the big lineaments in the Alps. And one thing that we have to keep in mind is that all this region was under a huge ice cap only 20,000 years ago. So this has many consequences. So if we start from the Aiguille Rouge fault, this is the paper from Hervé, Leloup, and co-authors. Just to situate the geology, we are in front of Mont Blanc here. The Aiguille Rouge is there. And this is a shear zone that was active for different orogenesis. If you look at this sketch from Michel Caran and co-authors, you see that there are many faults in this part, in this Chamonix Valley, which branch on this main décollement. Okay, and the main earthquake, historical and instrumental that happen in this region are located on this vertical fault up to 10 kilometer depth. And you see that this fault, which is localized here in France, continues in Switzerland, and all this microseismicity is present along the Rhone Valley in Switzerland for several tens of kilometers. So it's potentially a huge rupture fault. So we are not the first to study this fault, of course, but we are the first to have this nice image of the LiDAR, which allowed us to see this line very, very, very straight and continuous on several kilometers long. So from this line, we could, which is also under the vegetation, which is in steep places, we could have a look to the nicest place to study this deformation. And for example, you have two regions that I will explore. Firstly, this one and then this one. Whoop. So in the first region, we have a nice lateral moraine. Okay, all this was under the ice 20,000 years ago. And so this is the retreating stages of this glacier coming from Aiguille Rouge. And this is a lateral moraine that you see here in the picture, very straight. The problem here is this is the fault trace, and here the fault is a bit there are two branches which makes the width of the fault zone quite large, and so we can deduce that there's an offset, a lateral offset, but it's difficult to quantify how much. But it seems there's a deformation. What is interesting here is that we could date it. We could date this moraine at around 10,000 years with the cosmogenic, and so this gives us a chronological step. To precise the deformation, someone will recognize himself here. We looked at this this branch of the fault, this portion of the fault where the scarp is really sharp and continuous and narrow. And so here you can have you can reconstruct the topography looking at the gullies which are deflected of a few meters. So you see, this is an occasion of a workshop we did a few years ago. All these geologists mimic the geometry of the gully. And so you see between the yellow person and here, there are about 2-3 meters. And you see a small, let's say, uplift of the behind the fault. So this is for me a strong argument to say this is a tectonic fault, because we have right lateral strike slip, so it cannot be only gravitational or other processes. And clearly the lateral component is dominant. And here you see that the fault scarp with the shadow changes in height. This is because of the undulation of the topography. Okay, so if you are in this part and you dextral, you have a counterscarp here. Okay, if you are on the other side, you have no counterscarp. You have a bigger scarp on the same side. So this is a good argument for strike slip fault. We also observe this at the massive scale, because here is the same vision of before with the nice lineament. And globally, you see that here we observe this counterscarp. Well, this part is more elevated than here. And when you pass a saddle on this side, well, the scarp is on the other side. Okay, just with a cartoon is easy to understand that the two scarps on the opposite side. So here in the Aiguille Rouge, we have this information. We have post-glacial tectonic deformation. We have dominant texture strike slip kinematics. We could measure an offset, horizontal offset, or about 2.5 meters. Okay, we are not at 70 or 100 or like in Tibet, but there's an offset, and this means that this offset we have to create it with an earthquake that breaks at surface. So it means at least magnitude 6 or more, and this since 10,000 years. Now let's move to the south. The south is the Argentera or Mercantour Massif, and you see that in this region, okay, the seismicity is very concentrated here. Here is the Ubay region. And if you close up on this image, okay, you can follow this seismicity, and there are some stronger ones, around 5 in magnitude in the last century. And very interesting, you see that all these huge cloud of seismicity stops at this border. This is the bedrock massif. Okay, so where the bedrock appear, there are much less seismicity than in the sedimentary couverture. So we are again localized around the emergence of the Penninic front. Okay, this Penninic front was active for a million years, but now it's not more active as a thrust. But the deformation is still localized around him. So in this Argentera massif, we have this lineament, and we have many stages of deformation, as in Guy Rouge is a zone that was reused many times by tectonics. So for example, in Pliocene, there's clearly an extensional regime. During Quaternary, Quaternary, you have rivers plus dextral on this same structure. It's quite wide deformation zone, okay? And now what happens is nowadays, because it's since August, there's a swarm, a seismic swarm here in the sample of Ubay region. And so you see all these seismicity, there are several swarms actually in the last tens of years. And each time the main earthquakes are normal plus dextral, and also the present seismicity, there are a lot of extension and some dextral focal mechanism. Okay, so this is to keep in mind. Now let's move to the fault that we studied. So this is what we could see until 5-6 years ago. Let's say the old aerial pictures or satellites. So everybody can see that there's a lineament, but it's not so obvious. And when you are in the Alps, you are a bit suspicious of this lineament in terms of signification. Since 2-3 years, we have this LiDAR that covered the Alps and France. And so with the LiDAR, for example, we see this nice line, which goes very straight. Even here where the Isola 2000 station erased half of the outcrops, you still see some traces of this line, okay? So, and here we are in soft sediments, okay? We are not in bedrock. We can do even better with a drone now, and so we surveyed all this region. It's a plateau, like in Guy Rouge. We preserve this nice object in plateau, in high places in mountains, far from the erosion, far from the colluvia. And so in this place, 2 kilometers long, you again see this line very, very continuous. Here in this region, crossing this lake and these glacial deposits. So I will show you now what we did in this region. Also here you can see that as in the Guy Rouge, the scarp is continuous, but it's not always the same height, and sometimes the east is down, sometimes the west is down. So this is the view from the field. So this is to remember people were present in Patades. They are here 2-3 years ago, and so with this nice light of the sun going down, setting this sunset light, that the scarp is very visible here. Okay. So what we see is what I'm saying. This scarp is continuous, and when you are on the side sloping to the northwest, you see this counter scarp appearing every time. And when you are on the other side, the scarp is almost not visible. And also you have geomorphological objects like this, like an apple cut in two. So also this suggests very dominant strike slip kinematics. One other object at another scale is this paleo channel, which is not big, maybe just 1 meter wide, but when it rises on the fault, it parallelizes the fault, and before going again in its previous direction. So on this site, we have globally the same characteristics than in Aiguille Rouge, and which suggests cumulated dextral kinematics. we were convinced of the presence of the fault, but we said, okay, we can do geophysics to not to be sure, but to see if there's some signal that is visible a few meters below. And the answer is yes. When we do two profile of resistivity tomography, we see that at the fault scarp, below the fault scarp, here is few meters, here is maybe 20 meters. We see this conductory domain, which we explain like a more fractured zone filled by clays. I will show you in the trenches the clays, and probably the water and the clays give this conductivity. So the fault is also visible downstairs, and the electromagnetic field is on the same trend. So I go to the result of the trenches. This is the scarp seen in the field, the trenches that we did. Actually, this is not the first trench on the fault. There's been a trench 30 years ago, a bit farther to the south on the same prolongation of the fault. The problem is that this trench was done, if I understood well, very quickly because of the water, because of the authorization, and so the authors couldn't spend a lot of time on this trench. This is our trench where you see clear things, especially on this one. All this is the bedrock, very, very crushed. Here is gray, white, and on this side is colored, black, orange, white. And I think everybody can see that there's a step, and this step is very sharp. And this step is filled by colloidal wedge here in pink, and then other deposits come over this scarp. So the same thing on the other side, on the west wall, and you also can see that all these, let's say, bedrock is very flattened, is beveled by, we think, by the glacier that passed there at that time. So it makes a very nice marker, horizontal marker. And also this bedrock is filled of these clays, and these clays clearly are injected in the fault plane. And we think this is during the earthquake. This is because these clays are collapsed inside the colloidal wedge. I have a close-up on that. So you see in this part, this is the fault plane, and the clays. Sometimes we have chokes of the clays inside there, and all these pebbles clearly belong to a colloidal wedge. Interestingly, this colloidal wedge is not refaulted, and the geometry doesn't show it, and the pebbles are not rotated. So it looks like this is one event. So for me, this is it's quite clear. This trench looks very like matching the theoretical scheme of the seismic earthquake in a trench with this bedrock beveled, one deposit, and then the colloidal wedge over it, and an outwash on that. So we are looking for the dating. Now it's almost 2 years we are looking for that, but they say they are coming, so we are confident on that. What is interesting is that we have at least 1 meter of offset, apparent offset vertical, but we know that this fault is mainly strike slip. So to me, maybe you have another opinion, but to me this is a minimum, okay? Minimum offset for this fault, for this earthquake. So it means that the real offset must be more than one. Just very quickly, another trench, which is less clear, so I will not spend a lot of time on that, but which shows again that there's a flattened bedrock. And here we have two branches of fault, and each time is the northeast block, which is a bit uplifted compared to the south one. So I go to the conclusions. I think it's time. So here's what I talked to you: geomorphological evidence of post-glacial fault activity. Dextral strike slip, at least one, maybe more earthquake of 6.5 on this fault since 10 to 12,000 years. There are unsolved questions, of course. One is about the earthquake's recurrence time. The co-seismic slip, we have no information about that, unfortunately. And let's say philosophical question are, what are the link? This is your first question, between the present and the past seismicity, and what is the impact of the external forces on this fault activity. So this is the object of this INR starting now on the Alps, led by Christian Hsu. So if I resume these two questions in 2 slides and I finish, we know there are rotational movement in the Alps, okay, from paleomagnetism, from seismicity. So this is one driving force. The other one is, we know that Alps are going up in the middle, in the axis of the belt, but they are not convergent at all. Okay, so there are these vertical movement and this rotational movement. What is the main force there? And the other thing is what I was saying at the beginning. Okay, this is a tectonic load. There are 2 poles. We have to say, or maybe we have to tend to this answer. What are the earthquakes that are regulated by these tectonic forces in a, let's say, classical seismic cycle? And what are the earthquakes that are regulated by the external forces? For example, we know that ice loading can stop fault activity for a long time and then changes the stress in the crust. And so maybe the big earthquakes are linked to this. Or maybe the small earthquakes are linked to the fluids that are in the faults time to time. And I finish with this. Thank you.